Okay, so what we're going to be looking at now is that we're taking two sections and we're kind of putting them together. And the reason is because it's broken up into two parts. The fundamental theorem of calculus is there's part A and part B, or part 1 and part 2. And so we're kind of putting it all together into one big joined together one. That's going to be your fundamental theorem of calculus. Okay, so again, this is the fundamental because you got to be mental if you're not having fun with it. Huh. Okay. Theorem of calculus, the first part. Basically, if you assume that you have a continuous function in a closed interval a to b, and f of x is the antiderivative of f of x on ab, then to find this, all you do is you take the antiderivative of the function, this integral from a to b, you plug in the b, and then you subtract it from the a value. And that's basically the first part of it, and that's kind of the big part of this. So again, it's kind of finding the area under a curve. So if we look at this right here, and we want to find this graph down here, and we want to find the area from 0 to 4, okay, like what this one's showing. Well, here we can just count the blocks: 1, 2, 3, 4, 5, 6, 7, 9, 10, and then we got a half here, so 2 halves, that's 11. 12. So just by counting it, you get 12, which you can do if you have a nice straight curve. What we're going to do now is that we're going to use the integral from 0 to 4 of x plus 1 dx. Okay. And now we're going to solve this. So the first thing we've got to do is we've got to find the antiderivative of this. Well, the antiderivative of that using the power rule would be x squared over 2 plus x. All right. So now we are going to plug in a 4 into the x, so it'd be 4 squared all over 2 plus 4. And then we're going to subtract that from 0 squared over 2 plus 0. This gets us 0. The next one, that would be 16 over 2 is 8. 8 plus 4 is 12. 12 minus 0 is 12. So as you see, we still get our 12. And that's our area under the curve. So what the integral does is that it helps us find the area underneath a curve. Okay. And this is kind of the notation after you do the antiderivative, or the antiderivative of it. That's what it's going to look like. That's how it will be written. All right. So now let's look at this one. So this is a little bit different. We can't count this one like we did with the other ones where we counted the blocks. This one you're unable to. So now what you're going to do is you're going to use your integral. You're going to find the antiderivative. Oh, it should be dx. Antiderivative of this, which would make it right here 4x to the 1/4 plus 8, or 9 over 8x to the 8/3, and then we're going from 1 to 3, which is this region. So now we would plug in a 3 in for the x's. So we'd have 4 times 3 to the 1/4 plus 9 over 8, 3 to the 8/3. And then we would subtract that from 4 times 1 to the 4/3 plus 9 over 8 times 1 to the 8/3. Okay. And we would just calculate it through, and we'd end up getting our answer of approximately 21.2. Okay. So what you're going to do here is that you're just going to take the antiderivative of the part, plug in the first number, subtract it from plug in the top number, the end point, and then subtract it from the initial point, or the starting one. And you just subtract. And that tells you the area under the curve. Now let's look at this one. So we've got sine x dx from 2 pi to 0, or 0 to 2 pi. My mistake. 0 to 2 pi. So what we're going to do is that we take the antiderivative of this, which would be cosine. Actually, it would be negative cosine of x. We're going from 0 to 2 pi. And so now we'll plug in our numbers. Well, when we do this, what happens is that we end up getting 0. Okay. And you're thinking, well, how do we have an area of 0? Well, the reason for that is because of the curve itself. Remember, with our area, what's happening is that this area is positive on the top and negative on the bottom. And so if we have the same amount of area above the x-axis as the bottom, or underneath the x-axis, what happens is that they cancel themselves out. So with this integral, we're not finding the entire area between the curve and the x-axis. We're finding basically the positive or the negative area of it, okay? And kind of finding the difference that it cancels itself out. And so in this case, with a sine curve, it's the same area on the top and the bottom. They cancel themselves out, getting us a 0. So in this case, our integral is 0. But our total area between the curve and the x-axis, if we want to think of area as a positive number, is not 0. Okay. All right, looking at this one. So we want to take the antiderivative of this function, which would be natural ln of x. Okay. So then we'll go from -1 to 1. And if we're trying to calculate this, we're not able to. Okay. And the reason we're not able to is because this original function 1 over x is not continuous. So since it's not continuous from in our range, if it was continuous from -1 to 1, we're able to do this. But as you see, if we go from -1 to 1, it's not continuous. We have this vertical asymptote. So kind of the area in which we are incorporating kind of goes off forever in both directions. So with this problem, we are unable to find what it is because it's not continuous within our interval. Okay. All right. Now the next fundamental theorem of calculus, part 2, because you got to be mental for it not to be fun. Could I be any more hilarious? Anyway, assume that f of x is continuous in an open interval, blah, blah, blah. Basically, all this is saying is that it's the area of it. And if we want to find the derivative of the area, or the area derivative of it, it's the same as us just taking the derivative of the function, taking whatever the top value is and plugging it in. Okay. Furthermore, this satisfies that f of x, the initial condition that if you plug in an a, you get 0. Okay. We'll see an example of this. Well, this is basically the second part of it. Kind of saying, okay, it's the area. If we take the derivative of it with where we don't really know the endpoint, okay, we're given x as the endpoint, we can kind of just plug it in. So if we have this one right here, we have a of x is equal to the integration from 2 to x of the square root of 1 plus t to the third dt. Find the derivative and calculate the following: a prime 2, a prime 3, and a of 2. So a prime 2, well, remember a prime of x is just f of x. Okay, so just the number on the inside. And so what we'll have is that a prime, which is 2, we're going to go the square root of 1 plus 2 to the third, which would get us 3, square root of 9. Okay, that is our a prime 2. Now a prime 3, we're just going to take the number on the inside, or the function, and plug in a 3. 3 cubed, 27, plus 1, 28, square root 28. Okay. Square root 28, that could probably be simplified, but square root 28. And now the last one, we're going to take this 2 and plug it in for this x, and then we're going to do the integration. So it will be a of 2, which is from 2 to 2 of the integration of 1 plus t squared, or no, t cubed dt. Now if you remember, if we take anything from, if the original and the initial and the endpoint of our integration is the exact same, it always equals 0. Okay, and so that's what we have for these. Okay. All right, if we want to find the derivative of this function, basically all we're going to do is that if we take the derivative of gx, okay, so we want to find g prime of x, what's going to happen is that we have the sine of t, okay, but instead we're going to take the integration, or we're going to say it's sine of x, but what happens is that we're taking this and plugging it in. So it's going to be x squared. Since this is not just x, we have to use the chain rule. So we're going to multiply this whole thing by the derivative of 2x, which will get us g of x, g prime of x, is equal to 2x sine x squared. Okay. All right. So again, we get our g prime is equal to 2 sine. So what will happen is that you kind of have to use the chain rule here. All right, here's your IRAT. So this is what you're going to have completed. So the first part, you just have to do the integration for these three. Okay. So just find the integration, find what it comes up as your actual number. Okay, for each of these three. The last one, this is using the fundamental, the first part of the theorem, part 1. This is dealing with part 2. Okay, and what you're going to be doing is that you're going to find the formula of the functions represented by this integral. Okay. So it's like what we did in the very last one. You're just going to plug it in and you're just going to see what you get. Okay. And so hopefully this is helpful. We'll be moving on and going over more things with this integration stuff a little bit later.